Hi there, welcome to this lecture series on matrix algebra. Today we'll go through lecture number 8, part 1. The topic is linear map. In this lecture we will consider the matrix multiplication and view it in a more abstract setting as a linear mapping. Okay, so let's get started. Now let's consider a matrix A, which is a matrix of the dimension m by n. And then we know that A can multiply on the left with a vector and turns it into another vector. So we want to define this as a transformation or as a map. Okay, so the map is defined as follows. The transformation takes a vector Rn, meaning a vector of length n, and transform it into a vector of length m with the following operation. So y equals the transformation on x, which is the A matrix times x. To be more specific, we can write out the elements in this vector and the matrix. So this is the vector x. Now x is now transformed into a vector we call y. The y has dimension m, x has dimension n. They don't have to be the same. And then the y is obtained as the matrix A. Here we write out in detail is m by n matrix, and is this matrix A times the vector x. So you know this product will give you another vector with the length m, which we call y. Okay, so we think this as like a map. You take one object x and then you map it into a different map, and it's this element y. So we mentioned the term a linear map. So let's define this concept of linearity. What do we mean by a transformation being linear? So here's the definition. I have a map T, maps from Rn to Im, and this map is called linear if the following holds. That is, given two vectors u and v, they're both in Rn, and then another number, any number c, which is r, it's just a real number, will have the following. So if you multiply the vector v with a constant c, and then the transformation of that equals the transformation of v first, and then do the scalar multiple of c afterwards. Second property, if you add up u with v and take the transform of the summation, and it equals to the summation of transforming each. Okay. Let's look at this property in graphs. So what does it mean, the property 1? Well, the property 1 says that if you have a vector v and you do a transformation, this arrow means transformation, and you get t of v. And then the vector, a constant c times v, let's say c is about twice or three times as long as v, so that will be c times v. If you think in terms of vector, this is a vector pointing in the same direction, but it gets longer, right? Then the transformation of the c times v is exactly a scalar multiple of the transformation of v. So in this space, that is the transformed space here, so the result will just be taking this vector and in the same direction make it longer. That is a scalar multiple of this vector. Okay, so that's the first property. And the second one here, so we can take the example again with like two vectors in 2D. So if you have a u here and you have a vector v here, then you know that u plus v will be this vector. So you take u and then go v, or you take v and then you go in the direction of u, where you end up is u plus v. And the linear property says that this vector u plus v, and if you transform it to here t of u plus v, it's simply equal to the sum of the transform of each. Okay, so you can take the v and transform it, and then you get t of v, and take the u and you transform it and you get t of u, and then you add these two up, so tu and then tv, and then the sum tu plus tv is exactly t of u plus v. Okay, so let's make the claim that the map, the multiplication of a matrix, so t of v is a times v, the map is linear. Okay, so we can carry out a simple proof per definition to see if this map satisfies the two conditions of a linear transformation. So the first one, I want to show that take a c, that's a scalar multiple, transformation of c times v, what does that equal to? Well, that is, the transformation is just a times whatever you send in for me to transform. So a multiplied by c times v. And since the c is a scalar number, I can move it out. So it becomes c times a times v. And then a times v is just the transformation of v. So that's the first property. Now the second property, transformation of u plus v. Well, this is, so we take the u plus v here and we transform it, so it's a times u plus v. And then we use the distributive property of a matrix product, and it becomes au plus av. I can distribute the a onto each. And then au is just transformation of u, and av is transformation of v. So that's the second property. So we just have shown that this map tu is a linear mapping. Okay, so let's take a closer look at the 2 by 2 matrix. And the transformation, if you multiply a with a vector, so a would be multiplying onto a vector of length 2 here, and then you return the vector of length 2. So we say this is a transformation from R2 to R2. Okay, and the y here will just equal a times x. And if we write out the elements, that's the A matrix, that's the x vector, and you carry out this product, we can write out each element for the y. So y1 will be that, and y2 will be that. Okay, so to better understand this transformation, we can see, we can check first its effect on the unit vectors. That is, the unit vectors pointing in the direction of the axis. So they carry special symbols. So E1 will be unit vector in the x1 direction. So it's 1, 0. And E2 will be pointing in the x2, or we're familiar to call this the y direction. So it's the vector 0, 1. So perform the linear transformation T of E1. It would equal to A times E1. And let's put the A matrix here, multiply by this unit vector. And then we see that this one cross that give me A, and this one cross that give me C. So it simply takes the first column of A. And a similar calculation can be performed on the second unit vector E2. You carry out this product, and then what you get, you see that it returns the second column in the A matrix. Okay, so to put it into the proper vocabulary, so to speak, you would say that the columns of the matrix A, these columns, are the images of E1 and E2. The images meaning where they will land after they're being mapped. And now a similar thing happens when you have a more general matrix A. Let's say A is a m by n matrix. Let's write out its element like this. And what does it do to the unit vectors? Let's take a look. Okay, let's consider the unit vector which has 1 on the first element. So 1 and then all 0. And you carry out this product, and you see that what you get is a vector which is exactly the first column in A. And then let's say we have this unit vector which is 1 in the second element and then 0 otherwise, and you carry out this product. So this cross that will give you only this non-zero. So you see that you get the second column. So it's similar to the 2 by 2 matrix we have seen. And then you can go through all of them and reach the last one, the nth. Then you see that this product here will only take this value because that's the only non-zero, which is 1 here. So the resulting column vector will be exactly the nth column from the A matrix. Okay, so therefore this is like a general property now. For the map Tx defined by y equal ax, then the columns of the matrix A are the images of these unit vectors E1, E2, and En. So that is the A matrix. If you write out each column of the A matrix, it's the transformation of E1, the first column, transformation of E2, the second column, and so on and so forth. And the last one is the transformation of En. Okay, so let's take a look at a geometric interpretation of a linear map. This one can do in a mapping from R2 to R2 because it's a two-dimensional plane and we can draw the vectors and visualize it. So, okay, so let's say this map y equals ax. Let's say A is this matrix, A, B, C, D, general, just some numbers. And what does it do? Well, so we know that the columns will be the image of the unit vectors. Okay, so let's look at the unit vector E1. And we know E1 will be mapped into the first column, so A and C. Okay, so then we can find the position A and the C. Let's say it's here. So this one now becomes the image of E1. Okay, and now let's look at E2, which is like this kind of a y direction. And then this one will be mapped into the second column, B and D, right? So then we can find it here where it's B and D. So let's say this is B and this is D, and then that is the image of E2. So if now you take the little square, a unit square here in the first quadrant in this x1, x2 space, this little unit square is now being mapped to this parallelogram, because now this line is mapped here and this line is mapped here, and then this whole area becomes this whole area. Okay, so you can see that a linear map from R2 to R2, what it does to a region is that it kind of deforms it and possibly rotate it. So we can take a closer look at exactly what happens. So one special transformation would be the following, that the image of one of the unit vector doesn't change and the other changes, and it in the material science language, it would be you apply some force to transform it into, make it like shift a bit. It's called a shear transformation. So let's look at a matrix. Look like this: 0, 1, 0, lambda 0 for some number lambda. And let's check the image of E1. T of E1 is A times E1. If you work this out, it's 1, 0. So it doesn't change. It copies the first column, which is the same as E1. And then look at T times E2. So multiply by this one, I will get lambda 1. And lambda is some number. Okay? Maybe think it's a small number, a positive number, let's say between 0 and 1. Okay, so geometrically, what does that mean? Well, that means this E1 here is mapped to E1, it's the same. But then the E2 here is mapped to lambda 1. And then is this vector, which is lambda, some value. It's being shifted a little bit in the y1 direction. And then this unit square here in the x1, x2 plane is being transformed into this shape, which we call this a shear transformation. Another transformation which is important would be we want to transform something without applying any shear. So this will keep its shape and it will just be rotated. Okay, so let's take a look. So we want to transform let's say a little unit square here into also a little unit square, but is rotated by angle theta in the clockwise direction. Okay, so it's rotated by angle theta. So that means the E1 here will be TE1 and the E2 here is TE2. And we want to identify the A matrix, the 2 by 2 matrix, that will make this rotation. So since we know that the columns of the A matrix are the images of this unit vector, it's quite easy to find those columns. So A times E1 would be 1, 0. A times 1, 0 shall be the first column of A, and then it should be this vector. So what's the coordinate of this vector? Well, in the y1 direction here is just 1 times cosine theta, right? And then the y2 value for this point will be sine theta. So this is cosine, sine. Now let's look at the map image of the mapping on E2. And that will be this one here. So what's the coordinate of this guy here? Well, the y1 coordinate is now, this is the angle theta, is the same here. So it will be the sine theta, but it's negative, so negative sine theta. And the y2 element here will be the cosine theta. So we get that. Okay, so once we have found the images of E1 and E2, and we know that those would form the 2 columns of the A matrix, and collecting these 2 columns here, we can write out the A matrix. So a matrix like this just rotates the image by angle theta. Oh, actually it's counterclockwise. Okay, so that's all for the first part of this lecture. In the second half, we will look at the composite mapping, and we will take more examples of linear mapping and looking at properties of linear mapping. Okay, so I hope you enjoyed this one. I'll see you later.